Okay, I think it will be a good time to start the last session of the day. So welcome to the session. We have 3 talks. The first one is by Jugal Garg. I remind you that if you have questions, please put them on the chat box and I will read them. And later you have also the option of writing in the Slack. So Jugal, you're welcome to start.
Hello. Okay. Thank you, Yossi, and hello, everyone. So let me share my screen. Okay. So in this work, we designed the first strongly polynomial algorithms for linear exchange markets. And this is a joint work with Laszlo Weg. So let's begin with the market model, which was just a second, my slides are not. Okay. So yeah, so let's begin with the market model, which was introduced by Walras in 19th century. And in this market, there are n agents and n divisible goods. So divisible means like one in like milk, cake. So where we can divide 1 unit of goods among multiple agents. Like 1 unit can be like half unit can be given to one agent, 1/3 to another agent, and so on. And each agent I brings 1 unit of good I and has a linear utility function. Uij is the utility from the entire unit of good j, and if we are giving him like giving our xij amount of good j, then her utility is uij times xij, and then you sum over all goods. So this is the agent I utility when xij amount of good j is allocated to her. So what happens in the market? Given prices of goods, agent I earns pi because agent I brings 1 unit of good I. So the market price is pi. So she will earn pi dollars. And from this money, she wants to buy an optimal bundle. Optimal bundle means like which maximizes her utility function. So this utility function. So she wants to purchase a bundle which maximizes her utility function. And P is called equilibrium if market clears. So meaning that like the demand of every good meets its supply. So equilibrium is nothing but like prices and allocation. So let's say Pj is the price of good j and Fij is the money flow from agent I to good j, and it has to satisfy these two conditions: optimal bundle and market clearing. So optimal bundle in case of linear utilities is nothing but like this formula. So let me first like explain. Let's first understand what do we mean by Uij over Pj. What is the meaning of Uij over Pj? Uij is the utility for the entire unit of good j, and Uij over Pj is the rate of utility per dollar of money. And you want to purchase, if you are purchasing this good, then you want to purchase only if this good is giving you the maximum rate of utility, because you want to maximize the utility function. So these are called maximum bang per buck goods, because because you want to purchase only the maximum, the goods which has the higher rate of utility. So this is the optimal bundle condition for every agent. And market clearing is nothing but like the total money agent I is spending should be equal to her budget. So PI is the budget of agent I, and this is what she is spending. And the total money coming to a good for every good equal to PJ, because there is 1 unit of goods in the market, and so this good should get PJ amount of money. So F and P, if satisfy these two conditions, optimal bundle and market clearing, then it is an equilibrium. And the computational problem is to find these prices and allocation for a given market. So we can interpret this problem as a network flow problem. So the network flow interpretation is like this. So on the left hand side there are goods, and on the right hand side there are agents. So we want to find these prices P1 to Pn for these goods, and these prices then translate in budget, because like agent earns whatever is the prices, and they can only spend on MBB goods, because this is like this imply optimal bundle, because they only want to spend on the MBB goods. And let's connect all the goods to a source and all the agents to a sink. And if we can saturate all these edges, like that means like the total flow in the network is summation Pj, then this will also saturate this thing. Then these two conditions satisfy market clearing, and together we have an equilibrium. So one thing to note here is that this network is not fixed. as you change the prices, this the MBB edges will change. So the network will change with respect to the prices. So this is so network will change, right? So let's take a simple example. So suppose there are two agents and two goods, and the Alice brings one orange, 1 unit of orange, and Bob brings one unit of apple, and these are their utility functions. So Alice has 2 units of utility for orange and 1 unit of utility for apple, and Bob only likes let's say orange. So suppose like prices are one. Suppose like we try whether these are equivalent prices or not. So suppose we set prices to one and one. Then what happens? They will earn budget, the price translate into budget. And what is the MBB goods for Alice? So the rate of utility from orange is 2/1, which is 2, and the rate of utility from apple is 1/1, which is 1. So she only wants orange. And Bob anyway likes only orange, so he will only demand orange. So you can see that this will not clear the market because we won't be able to clear the supply of apple, and there will be more demand for orange. So this is not an equivalent prices. But now suppose we set prices to 2 and 1, then this will translate into budget 2 and 1, and then at these prices, Alice, like the girl, is indifferent between both the goods because like the rate of the utility is 2/2 for orange, which is 1, and the rate of utility from apple is 1/1, which is also 1. So she's indifferent because she gets the same rate or maximum rate of utility from both the goods, and Bob anyway likes orange. So these are the MBB goods, and then we can see that we can saturate or we can send this flow with the spending $1. Alice is spending $1 on orange and $1 on apple, and Bob is spending $1 on orange. So this is an equivalent. And this problem has been extensively studied for more than half a century. So I will not go over this list, and this is not an exhaustive list. I just want to point you two things. One is that there is a very important special case, which is which is itself well studied. It's called Fisher markets. The difference is that in the Fisher markets, every agent brings fixed amount of budget. So agents are bringing budget, not the endowment. So they have a fixed amount of budget, and I will be using the Duane-Mellon weekly polynomial algorithm as a subroutine in our algorithm. So the Duane-Mellon algorithm extends the DPSV algorithm for Fisher market. So let me just give you one slide overview of these algorithms. Then we will talk about my algorithm. Okay, so DPSV algorithm is like this. So here the difference with the exchange model is this: the budget is fixed. So this is a fixed budget. This is a constant. And we still want to find the prices where agent is spent on MBB goods, and you can saturate all these both the sides. So what DPSV algorithm does, it starts with a tiny price. So you start with a tiny price and such that the max flow is summation pj. So it starts with very small prices such that you can saturate all the edges out of the source. Okay, so what are the invariants they maintain? And they of course this may not be saturated the right hand side because they may have surplus. So invariant is that they keep increasing the prices. They keep increasing the prices of the goods, and they maintain that all these edges are remain saturated. So all the goods are fully sold. Is the same thing. So they maintain this invariant, and they try to minimize the surplus. And surplus is the unused budget. The buyers which are not able to they are not able to spend the remaining budget. If you can saturate all the right hand side, then you are done. Then we are done, right? So these invariants imply that the L1 norm of the surplus, that means the total surplus, monotonically decreases, and also the L2 norm of the surplus monotonically decreases, and the progress is measured in terms of the L2 norm. So they claim that or they show that the L2 norm decreases geometrically, and this gives them the weekly polynomial algorithm. So now let's talk about the Duane-Mellon algorithm. The setting remains the same, but now it becomes more challenging because these budgets are not fixed. These are the prices. This depends on the prices. So they also start with the tiny p, but they cannot saturate all these edges, because if they saturate all these edges, then of course you are done. So they start with the tiny prices, and they also increase the prices monotonically. So prices only increases, and they also maintain that the L1 norm of surplus monotonically decreases. But the L2 norm of surplus can go up and down. So this is the main difficulty. We cannot show that the L2 norm of the surplus decreases monotonically, and that's why the progress is like is a clever combination of prices and L to norm. So either prices increases substantially or L to norm decreases substantially. So they combine these two measures to derive a weakly polynomial. But both these algorithms are weakly polynomial time because like the progress is measured in terms of geometric decrease in these quantities. So we derive an strongly polynomial algorithm. So there is a question: how do you increase the prices? You choose the set of goods carefully for which the demand is more. So you take a subset of goods for which the demand is high. So I will not go into that detail, and then you increase those prices. So you maintain that whatever prices you are increasing, they will be fully sold. So because you want to like maintain the surplus decreases. So you just increase the prices of those goods for which you can generate money, so that this remains the main cut. Okay, so these are weakly polynomial algorithm, not the strongly polynomial algorithm. So let me just give you one slide like a description of strongly polynomial algorithm. Suppose in the problem there are n integers in the input and each has value at most c. So we said that an algorithm runs in weakly polynomial time if the running time is polynomial in n and log c. So this is the definition of weakly polynomial time. For strongly polynomial time, we want the algorithm to run in polynomial in n. So you can see it should not depend on the size of the encoding length of the numbers. As an example, let's consider linear programming problem. So this is the linear programming problem. And let's say A has m constant, m by n, and n variables. So the total number of numbers, like the input is like mn plus m plus n numbers, right? So B is m, and the m numbers, C is n numbers, and like and A is mn numbers. So this is the input. And let's say L is the encoding length of all the numbers. So in a strongly polynomial algorithm, we want the algorithm to run in polynomial in n and m. And in weakly polynomial algorithm, you can allow it to take to take time polynomial in n, m, and l. So the ellipsoid algorithm and interior algorithm, they both are like weakly polynomial algorithm. And in fact, this is a major open question in optimization whether there exists a strongly polynomial algorithm for linear programming. Okay, so let's come back to our problem. So we design a strongly polynomial algorithm for linear exchange markets. So the first observation is that suppose like we look at the support of the equilibrium. Support means like all the MBB arcs. Suppose someone gives me all the MBB arcs at equilibrium. So let's say F star is the set of MBB arcs at equilibrium. Then we can compute equilibrium in a strongly polynomial time. So I don't need to know the prices and like allocation. You just give me the MBB arcs, I can just find prices and allocation in a strongly polynomial time. So our approach is based on this fact that we just need to learn F star. So we will gradually find F star. We will gradually find arcs in F star, and we will call them revealed arcs. So the arcs which are revealed in F star, we call them revealed arcs, and we will keep increasing the set of revealed arcs. So let's say F is the current set of revealed arcs. Initially, it is empty set because we don't have anything, and we will just keep building it to F star. One crucial thing we do is that we allow F to carry negative flow. So of course, we allow F to carry negative flow, and it will be clear in a moment like why this will be very useful. Okay, so the question is like how to find even one revealed arc. So this is the first thing we need to ask: how to find even one revealed arc. So this is the setting. So this is the network flow characterization. So we prove this lemma that if you give me any prices, doesn't matter whatever prices you set, but if some arc, some MBB arc, if it carries large amount of flow, so large means the flow on arc is more than total surplus, total unused budget. The surplus is the unused budget. Then this arc will be there in F star. So you just give me like any prices, but just make sure that some arc carries very large amount of flow. Then we claim that this arc will be there in the equilibrium support, in F star. Okay, so this is very good. So our goal is to make some arc outside F, because F is already revealed. We want to make some arc outside F to carry large amount of flow. When this happens, then we know that this arc is part of the F star. We will extend F using this arc because of this lemma. At this point, you can run the DM algorithm. This arc can be found if we run the DM algorithm, but it will take tons of steps. It will be taking weakly polynomial number of steps to give you one more arc. and we want to boost it. We don't want to keep running DM steps like slowly because it will take very long time. We want to give it a boost. So what do we mean by boost? We want to find the best solution for a given f. We have the current set of revealed arcs and we want to find the best solution for this set of revealed arcs. So what do we mean by revealed best solution? We want to find the maximum possible prices such that the surplus is bounded and arcs in f are MBB and there are no flow outside f. So we want to send flow only on f. So this is the f in the diagram. There are other MBB arcs but which are not revealed. F is a subset of all the MBB arcs. So f is revealed and we want to send only flow only on f and want to maximize the prices. So this is the problem we want to solve, and we show that if you have such a solution, the best solution for a given f, and if you run the DM algorithm starting from this solution, then within a strongly polynomial number of iteration, there will be one more arc that will be revealed. So we are almost there, right? We just need to find the best solution for a given f. Then we are done. But the best solution for a given f turns out to be a LP. And here we crucially use the fact that we allow negative flow on f. Because if we allow negative flow on f, then we can write the best solution for a given f problem in terms of only price variables. We don't need to worry about the flow variables. So we can write this problem as a price variables. So here what we want to maximize the prices. And this is the MBB constants. The arcs in f should be MBB. And this is the bounded surplus. The surplus should be bounded. And this is the LP we want to solve. And if we can solve this LP in a strongly polynomial time, then we are done. We can just like, based on the previous lemmas, we get a strongly polynomial algorithm. But how to solve this in a strongly polynomial time? We don't have a strongly polynomial time LP solver, right? And this LP does not belong to the special classes of LP for which strongly polynomial time algorithms are known. Excuse me. So our approach is we devise a strongly polynomial algorithm to solve these kind of LPs approximately. And this approximate solution will be good enough for our purpose because like we can run the DM algorithm a little bit longer to make up for this approximation. So for that, let's recall the classical result by Magiddo from 83. So suppose like you have a system of linear inequalities where every inequality has at most two variables. So like here, see that like every inequality has at most two variables. This has two variables. This has one variable. Suppose you have such a linear inequality system. Then he proved that like there is a strongly polynomial time algorithm to find a feasible point in this system. And in fact, this is the first paper which defined the notion of a strongly polynomial time. He called it genuinely polynomial. And moreover, if you have a system where like monotone two variable per inequality system, monotone two variable per inequality system, that means every inequality has at most one positive entry and at most one negative entry, then we can also maximize the summation of variables in a strongly polynomial time. So is this an empty BPS system? This is not an empty BPS system because this is constraint is fine. At most one positive entry, at most one negative entry. This is not, this has two positive entries. So this is not an empty BPS system. If you remove this, then it is an empty BPS system. So on empty BPS system, we can also maximize the summation of variables. So let's look at our LP. So this is our LP. We are maximizing the summation of variables, which is like good. And this is the MBB constant, which is empty BPS system, which is also very nice. But this is the problem. These constants are not even empty BPS. This is like many variables. So there are many constants like this. So these are the problematic constants. Otherwise, we would have been done using the existing results. So this is the problematic constraint. This is like many variables per inequality. So we prove a very general theorem. For that, we define a notion of Z plus matrices. So we say that a matrix M is Z plus if all of diagonal entries are non-positive. All of diagonal entries are non-positive and all column sums are non-negative. So this is an example of a Z plus matrix. So you can see that like all of diagonal entries are non-positive, and if you sum every column, this is like this has to be non-negative. So you can check it. So this is a Z plus matrix. So we prove this theorem that you give me a polytope. So P is a polytope where the constant matrix M is Z plus of this form, then we can construct another system of inequalities M bar P less than equal to B bar using Gaussian eliminations such that M bar is an empty BPI system and this the new polytope so, subsumes the original polytope P. So this is the new polytope and it is also contained inside a blown up polytope by alpha square. So you just blow up P by alpha square, then it is contained inside these two polytopes, where alpha depends on the B vector. It's like summation of Bj over minimum Bk. So this is the theorem we prove, and let's apply this theorem to our LP. So this is the LP formulation we want to solve. So these two constants are anywhere empty VPI. So let's write them as AP less than equal to 0. And this is the problematic constraint, MP less than equal to B. And we want to solve this LP. So this is the problem we want to solve. This is the boost problem. So what we want to optimize the summation of variable, maximize the summation of variable on the intersection of P and P prime. So P is the first polytope and the P prime is the second polytope. And we want to find we want to optimize summation of variables on the summation of prices on this intersection. And P is an empty BPI system, as I just showed you, and M is a Z plus matrix. So this is a Z plus matrix. So let's apply our theorem. So we can get a Q which contains P prime. I think it has to be okay. This is fine. Yeah. So Q contains P prime and is also contained inside n square times P prime, n square blow up of P prime. So that means that this is our intersection, but I can find Q using our theorem, and P prime Q over n square contains inside P prime because the alpha turns out to be n for our case. So now we are optimizing over this bigger intersection. Now this is the additional part. You can see that. Right? So we solve this problem maximize summation Pj over P intersection Q. Now it becomes an empty BPI system. So we can apply the strongly polynomial algorithm. And since it is contained inside n square, this gives an approximate solution for the original problem. And this approximation factor is within n square. So as I said, we are fine with this approximation because we can run the DM algorithm little bit longer. The overall algorithm is like this. You start with an empty set of revealed arc because initially there is nothing. Then you just give it a boost, find the best solution for this set of revealed arcs, and then you apply the DM algorithm on top of it. And we are guaranteed to find one more arc in a strongly polynomial time. Then we extend F and we keep repeating it until we find F star. And given a set of revealed arc, we can check in a strongly polynomial time because whether it gives a solution or not. So everything is strongly polynomial. So this is a strongly polynomial time algorithm. So since I have 2 minutes, so let me give you a recipe to build your own strongly polynomial algorithm. So for that, first you need to check, can we compute optimal solution if the support is given? If the answer is no, then this approach will not work. So given the support, you should be able to come up with a strongly polynomial algorithm to check whether it is a solution or not, or come up with a solution if it is a right support. Suppose the answer is yes, then you look at the subset of the support, some subset of a support, and then you need to find the best possible solution. Maybe approximately may also work because in our case we just find an approximate best solution with support inside F. So this is the first problem you need to solve, or maybe second problem. And once you can solve this in a strongly polynomial time, then you run then you start from such a solution and run the whatever non-existing weakly polynomial algorithm, and then show that you can extend the set of revealed arcs or the support in a strongly polynomial. So let me stop with a summary and some open questions. So our algorithm is specifically designed for linear exchange markets, and there is a non-separable convex flow formulation for linear exchange markets. So we can also this convex formulation also can be solved in a strongly polynomial time, but can we design an algorithm for a broader class of convex programs? Can we design can we generalize this approach to solve a broader class, some a more general class of convex programs? And the second is we devised a strongly polynomial algorithm for approximately solving a LP, and I'm not aware of any such result. And can we generalize this result to further settings? So with this, let me stop, and I can take a few questions. Thank you.
Okay, thank you. So I see that there is a question here by Sabdif. What is the name of the method that uses the Z plus? Sorry.
Yeah, so we just use the Gaussian elimination. What do you mean by the name of the method? So we just use the Gaussian elimination to convert any polytope into another polytope with the constant matrix Z plus.
I think he wrote paper. I'm not sure if he wants to know the name.
Oh, this is the Z plus notion we define. This is not known. This is the we are defining this notion actually. So there is a Z matrix notion, and we are just extending it to Z plus. So this is the first time we are defining. Yes.
Okay, more questions? Let me ask a question while people are still thinking. What's the polynomial? What's the running time approximately in terms of N and M?
So our algorithm, because we have like the same number of goods at same number of agents, like okay,
I see.
Because you can convert anything to this setting actually. So so our algorithm runs in order n raised to 10.
So you think that there is a much simpler algorithm or not?
No, actually the weekly polynomial algorithm by Duane-Mellon, that runs in like, I think, I don't remember exactly, but I think n raised to 7 or something, or 6 maybe. And so it's like already very high. Log u is the maximum utility value, and our algorithm runs in order n10 or something like.
I see. So David White's asks if there is any conditional lower bound on the running time, or you think that it's eventually it's going to be very high?
I don't know actually, because like for the Fisher setting, I think one should maybe improve the running time bound for the Fisher setting first actually. For the Fisher setting, it is already like n raised to 4 log n actually, yeah, something like that. Because Fisher is a much easier setting, like maybe, yeah, there is one actually, maybe you are right actually. One can, this is an interesting question, whether one can show some conditional lower bound for these problems. Yes.
Okay. And Sahil Singla is asking, can we find weekly polynomial algorithm for linear exchange market by using weekly poly-algo for convex optimization?
Yes.
Replacing the DM algorithm.
Yeah. So there are convex programming formulation for this problem. There are many convex programming formulation, not one. So you can use the whatever general purpose convex programming algorithm to solve those programs. And I think recently, like some papers have like get the best running time, the weekly polynomial running time. So this is, I think, yeah. So there are many convex programs, like there are many convex programs, and they are different convex programs. So the latest one is this one, and this is like a special. This is like a it is like all the constants are linear, only the convex objective. The other programs have like non-linear constants.
Okay.
Oh, so okay, so maybe I misunderstood the question. So yeah, for our algorithm, Lassie has replied. Okay, so yeah, you cannot use it to replace DM subroutine. We don't know. Yeah.
Oh.
You can, because there is a convex programming formulation, so you can just apply convex programming like solver for the convex program. Yeah.
Okay, thank you for the nice talk, and yeah, and I think we can, if there are more questions, please write them in the Slack, and you'll get answers. I hope, yeah. Okay.
Yeah, no, I will answer. Okay. Please write on Slack.
Yeah, okay, on Slack.
Okay, thank you.